Hi everyone, in today's video we are going to be coming up with an analogy for heat and mass transfer using the Lewis relation. We are able to relate heat and mass transfer because they act similarly in many situations. And so ultimately our goal is to find an equation that relates both our mass transfer coefficient, which is K sub C, and our heat transfer coefficient, which we know as H. And so we have many different dimensionless numbers that come up with heat and mass transfer from the Buckingham Pi method. And so for mass transfer, two of the dimensionless numbers that come up in mass transfer are the Sherwood number and the Schmidt number. The Sherwood number is the mass transfer coefficient K sub C multiplied by the length divided by your diffusion coefficient of components A through B. In word terms, this is equal to the convective mass transfer divided by the diffusive mass transfer. For our Schmidt number, that is going to be the viscosity divided by the density multiplied by the diffusion coefficient of components A through B. In word terms, this is the momentum diffusivity divided by the mass transfer diffusivity. Now for heat transfer, we also have two dimensionless numbers, and those are the Nusselt number and the Prandtl number. So the Nusselt number is equal to the heat transfer coefficient multiplied by the length divided by the thermal conductivity. In word terms, that is the convective heat transfer divided by the conductive heat transfer. And the Prandtl number is the heat capacity multiplied by the viscosity divided by the thermal conductivity. And this is equal to momentum diffusivity divided by thermal diffusivity. Now just taking a look at these different dimensionless numbers, we can see that the Sherwood number and the Nusselt number appear to have some sort of relation, as well as the Schmidt number and the Prandtl number. And we can mainly note that by just seeing that the Sherwood number deals with transfer and the Schmidt and Prandtl number deal with diffusivity. And so we can take this a step further and actually divide our Sherwood number divided by our Prandtl number, divided by the Nusselt number. And so if we do that, we can plug in our values here. This is going to be our mass transfer coefficient, K sub C, multiplied by the length, divided by the diffusion coefficient of components A through B, multiplied by the reciprocal of the Nusselt number, which is going to be our thermal conductivity, divided by our heat transfer coefficient and our length. So our length terms cancel. We're going to have heat transfer coefficient, or sorry, mass transfer coefficient multiplied by the thermal conductivity divided by the diffusion coefficient of components A through B multiplied by our heat transfer coefficient. Now we can actually write out experimental equations for the Sherwood and Nusselt number. So the Sherwood number is equal to the concentration multiplied by the Reynolds number to the 1/2 and the Schmidt number to the 1/3. Our Nusselt number is equal to the concentration multiplied by the Reynolds number to the 1/2 and the Prandtl number to the 1/3. So now, if we divide these two, we'll find that this is equal to the Sherwood number divided by the Prandtl number to the 1/3. And this value inside here is actually our Lewis number, which if you were to plug in values for water vapor, that would be approximately 1 for water vapor, which will be useful here in a second. So now if we put these together, we have that the Sherwood number divided by the Nusselt number is equal to the mass transfer coefficient multiplied by the thermal conductivity divided by the diffusion coefficient multiplied by the heat transfer coefficient. That is equal to the Schmidt number divided by the Prandtl number to the power of 1/3, which we said the Schmidt number divided by the Prandtl number was the Lewis number. And if you divide the Schmidt number by the Prandtl number, you'll have that is the thermal conductivity divided by the density multiplied by the heat capacity multiplied by the diffusion coefficient. This is to the power of 1/3, of course. And so this is also our Lewis number. So here we have our Lewis number as well. So now if we put this together, we'll have that we have the heat or the mass transfer coefficient divided by the heat transfer coefficient multiplied by the density times the heat capacity times our Lewis number is equal to the Lewis number, the Lewis number to the 1/3, which we said was approximately 1 for water vapor. So now if we divide this out, we are going to have that the mass transfer coefficient divided by the heat transfer coefficient multiplied by the density and heat capacity is equal to 1. If we want to solve for the heat transfer coefficient, we're going to have that the heat transfer coefficient is equal to the density times the heat capacity times the mass transfer coefficient. And so that is our relationship between our heat transfer and our mass transfer using that Lewis relation. Now we are going to derive and show the relationship between wet bulb temperature and the adiabatic saturation temperature. From this, we are going to derive an expression for the molar concentration of water in the air in terms of dry and wet bulb temperatures. And we're going to be using our equation that we just derived previously. Okay, so for this situation, our first scenario we're going to look at is evaporative cooling. Now to model this, we are going to imagine we have this flat surface. Oops. And this flat surface has a water bubble on top of it. And this water bubble has some temperature, we're just going to say is T sub W. And there's going to be air blowing over top of this water bubble. And this air also has its own temperature, which is going to be T sub air. Now we know we're going to have both heat and mass transfer. Now we're going to have heat transfer from the air to this water bubble. Now when that heat is transferred to that water bubble, we're going to have a mass transfer occur from the water to the air. And this is the molar flux of the water to the air. Now we can assume that this process is at steady state. And what that tells us is that the heat transfer and the mass transfer are equal to each other. So we can write out our equation for heat transfer. And this is going to be equal to the heat transfer coefficient H multiplied by the area multiplied by our change in temperature, which is going to be the temperature of our air minus the temperature of our water. That heat is being transferred from the air to the water. Now this is going to be equal to our mass transfer equation, and that is the mass transfer coefficient K sub C multiplied again by the area multiplied by our change in concentration, and that is going to be the concentration of the water to the air. That's going to be the concentration of the water minus the concentration of the air, which will put us C infinity. Now let's take a look at our units. So the units of this equation for our heat transfer are joules per second if you work this out. And our units for mass transfer is going to be in moles per second. Now, in order to relate these two equations and set them equal to each other, we need some sort of proportionality constant. And what we can use is the enthalpy of vaporization. The enthalpy of vaporization has units of moles per joule. Sorry, has units of joules per mole. So what we can do is we can actually multiply this mass transfer equation by this enthalpy of vaporization. So now I'm going to rewrite our equation. This is the heat transfer coefficient multiplied by the area multiplied by the temperature of our air minus the temperature of our water. This is equal to our enthalpy of vaporization multiplied by the mass transfer coefficient K sub C multiplied by our area multiplied by the concentration of the water minus concentration at infinity, or the concentration of the air. So now this is where our equation comes in that we had just derived. I'm going to plug in this for our heat transfer coefficient. So that's going to be the density multiplied by the heat capacity multiplied by the mass transfer coefficient. So we're going to have this be the mass transfer coefficient multiplied by the density multiplied by the heat capacity multiplied by our area. And then, of course, we have our change in temperature from the air to the water equal to our enthalpy of vaporization multiplied by the mass transfer coefficient multiplied by the area multiplied by the change in the concentration from our water to infinity. Now we can cancel some terms here. Our mass transfer coefficient term is going to cancel, as well as our area term. And so this means we are left with the density times the heat capacity multiplied by the change in temperature from the air to the water is equal to that enthalpy of vaporization multiplied by the concentration of the water minus the concentration at infinity. And this becomes our equation for evaporative cooling. Now for this second scenario, we're going to be looking at adiabatic saturation temperature. So we're going to be looking at adiabatic saturation temperature. And to model this, we are going to draw out a very long pipe. So we're going to have this really long pipe, and there's going to be water that covers this inner surface of this pipe. And there's also going to be air flowing through this pipe. Now, of course, there's going to be an inlet temperature for the air and the water. So the inlet temperature of the air, we're going to mark as T air 1 for the temperature going in, as well as TW1 for the temperature of the water going in. Now, because this is an infinitely long pipe, we can say that the temperature of the air that is leaving this pipe is equal to the temperature of the water that is leaving this pipe. And that is because at this point, the air has been fully saturated by this water. So the temperature of the air that's leaving has a concentration of water equal to 100%. And the relative humidity, which we'll put as RH, is also 100%. So it's fully saturated. And that is why we can say that the temperature of the air coming out is equal to the temperature of the water coming out. Now, of course, we also have heat and mass transfer in this scenario too, so we can write out a similar equation to what we did up here, just subbing in our different values for temperatures that are going in versus temperatures that are leaving. So for our heat transfer side, this is still going to be the heat transfer coefficient multiplied by the area. And this time it's going to be the temperature of the air that is entering the pipe minus the temperature of the water that is leaving the pipe. This is equal to, again, our enthalpy of vaporization because we need that proportionality constant, multiplied by the mass transfer coefficient, multiplied by the area, multiplied by our change in our concentrations. And this is going to be the concentration of air leaving minus the concentration of the air that is entering. Just like we did before, we can sub in for H, which is rho Cp K sub C. So this is going to be our mass transfer coefficient multiplied by the density, multiplied by the heat capacity, multiplied by our area, the air temperature going in minus the water temperature leaving. This is equal to our enthalpy of vaporization multiplied by the mass transfer coefficient in the area, multiplied by the concentration of our air that is leaving minus the concentration of our air that is entering. And what we can do is, once again, cancel our mass transfer coefficient terms as well as our area terms. So our equation for adiabatic saturation temperature, this scenario is going to be our density times our heat capacity multiplied by temperature of the air going in minus the temperature of the water leaving, which we said is the same thing as the temperature of the air that is leaving. This is equal to the enthalpy of vaporization multiplied by the concentration of the air that is leaving minus the concentration of the air that is entering. And so as you can see, we have pretty similar equations between both of these. So now we can look and relate our two equations. So in our first equation, we have our concentration of water at the vapor phase going to the concentration of our air, or C infinity. This term here for the concentration of the air leaving is related to the relative humidity at 100%. And this term here is related to the concentration of our relative humidity at 100%. So now what we can do is we can plug in these values to find our concentration and our temperatures that we don't know. And by doing this, we can solve for the molar concentration of water in the air currently and not when we're at 100% relative humidity. And so if we plug those values in, we're going to find that the concentration of the air that is leaving that pipe minus the concentration of infinity is equal to our density times our heat capacity multiplied by the temperature of the air minus the temperature of the water, all divided by our enthalpy of vaporization. And back to our original point in our equation, we wanted to find the molar concentration of water and air in terms of the dry and wet bulb temperatures. So if we're looking at our dry, we're going to be solving for this C infinity term. So if we do that, this is going to be C infinity, so that molar concentration is equal to the concentration of the air that is leaving that pipe minus the density times the heat capacity times the temperature of the air minus the temperature of the water divided by our enthalpy of vaporization. And if we're looking for that wet bulb, molar concentration, that is going to be the concentration of the air that was leaving that pipe, which is equal to that concentration at infinity plus the density times the heat capacity times the temperature of the air minus the temperature of the water, all divided by the enthalpy of vaporization. And so that is homework 5, part A.